Okay, so in this part of the lecture, we're going to look at polynomial regression and step function regression. And we'll start with polynomial regression, which of course we've encountered before. We've seen it in lecture 4, and in lecture 6 we talked about it as a means of considerably expanding the scope of the linear model to incorporate nonlinearities. And in lecture 8, in the context of generalized linear models, we also looked at polynomial linear predictors within the generalized linear model context. So, as I said, we're going to deal just with a single covariant because that's going to improve our focus here, which is simply on nonlinear relationships. So we'll simply focus at the moment on one. And we know that the standard linear regression model, comprising a response y and a single covariate, as introduced in lecture 4, takes this form here. And polynomial regression, as we know, simply extends this model by incorporating a polynomial function of x into the regression equation. Now, a polynomial function takes the form shown here. This is a polynomial function of degree d. So each term in the function is the product of a coefficient, beta j, and a non-negative integer power of x. Okay? And the maximum integer power in this equation is d, and we call a function, we say that a function is of degree d if that's the maximum integer power that is placed on x. And we define subclasses of polynomial function classified according to the degree of the function. So when d equals 1, we have a linear function. This is the function shown here in regression context. A quadratic function, d is 2. So we would add on in regression plus beta 2 xi squared. Cubic function d equals 3, we'd add on beta 3 xi cubed. And a quartic function d equals 4, the degree of the polynomial is 4, we would add on beta 4 xi to the power of 4. So that's a polynomial function. Polynomial regression is therefore simply any linear parameter specification that takes a polynomial form. Polynomial up to degree d, whatever d is. And for a large enough degree d, a polynomial regression allows us to produce a highly flexible nonlinear curve. And we've seen this actually before. In practice, it's unusual to use a d greater than 3 or 4, so cubic or quartic, because the polynomial curve can become overly flexible and actually take some quite strange shapes at the boundary. So 3 or 4 is the usual way it's done, but there's no specific reason why we need to limit it to 3 or 4. So the polynomial regression model can be written in matrix form in this expression here. So we have, our column vector of y, we have intercept term, design matrix, for x here with an intercept term in the first column, and then the different powers of x to the power of 1, x to the power of 2, up to x to the power of b, coefficient vector, error vector, and that's all. And this just demonstrates that, as we said, I think in lecture 5, the polynomial regression form can just be treated as a multiple linear regression with d covariates and estimated in that way. And the parameters vector beta of that model can be estimated via least squares as normal. So that's it. I won't say any more about polynomial regression because we know what it is and we've seen it before, but it is important in what we're about to discuss today. Very important actually. So let's look at an example of polynomial regression. And the example I'm going to use throughout this lecture to demonstrate nonlinear relationships uses some open air quality data that's available in R. And the question that we are principally interested in is, how does temperature, air temperature, affect the atmospheric concentration of nitrogen oxides? Now, the relationship between nitrogen oxides concentration and temperature is often thought to be non-linear due to the complex nature of NOx emissions, chemical reactions, atmospheric processes, and so on. And in this slide here, I've written down some reasons why we think that the relationship should be non-linear. This isn't a lecture on the chemistry of NOx concentration and dispersal, so I don't need to go through these. All I need you to accept here is that we do not expect the relationship between temperature and NOx concentration to be linear. We think it should be non-linear. And so for that reason, if we want to understand the nonlinear relationship, that's actually important. It's important to represent it nonlinearly because understanding this relationship is important for air quality modelling, for regulation compliance assessment, and for the development of effective emission control strategies. And for that reason, when people model this relationship between NOx concentration and temperature, they tend to employ flexible modelling techniques to do it. That's why this is a good example, because it's one where it's really these semi-parametric and polynomial forms that we're going to talk about today are used in the real world. So the open air data in R, which you'll be able to access, provide hourly data from several hundred air pollution monitoring sites in the UK. And the data record many things: the name of the monitoring site, they give the site a code, the date, crucially for us, nitrogen oxide concentration, which is going to be our Y variable, dioxide concentration, ozone concentration, and so on. You can read this list yourself. But it records air temperature in degrees Celsius, and that's going to be our X variable. So, the first thing we do is we plot the data. This is a scatter plot of air temperature, which is our X variable, against NOx concentration, which is our Y variable, from a monitoring site near Imperial in North Kensington in 2022, and it's shown below. And what this scatter plot indicates is that the theory we discussed above, so this theory here that says we expect things to be nonlinear, looks like it might have something to tell us, because the scatter plot indicates that the relationship may be nonlinear. And so to capture this nonlinearity, we're going to propose a fourth degree polynomial regression of oxide concentration on air temperature. I'm going to estimate this model simply by least squares, because that we know is blue in this context. So here's some R code for polynomial regression. We load the library, open air, we open the data, we remove missing values, so we prepare the data, we plot it, and this code here will just give you this plot here that you've already seen. And then we fit a polynomial regression model. Linear model, NOx is our dependent variable, air temperature is our independent variable, and we use this syntax here to tell R that we want a polynomial of degree 4 in air temperature. And this gives us the results that you can see here. Usual thing, we get the call, we get the some statistics on the residuals, their quantiles, coefficient, estimate, the standard error, the t-value, the p-value, and some diagnostics on goodness of fit, as usual. So we've seen it all before. Now each coefficient of the polynomial is statistically significant, as we can see here from the t-values and the p-values, supporting the hypothesis that a nonlinear fourth degree polynomial provides a suitable fit. But actually, when we interpret these results, these individual coefficients aren't of particular interest, because we're modelling a single independent variable. We're not interested in 4 independent variables. We've only got 1. So what we want to do is we want to look at the entire fitted function across a grid of values. That's going to tell us how the fitted curve looks across the support of temperature in order to understand the relationship between temperature and NOx concentration, in order to see the nonlinearities in the relationship itself. So to do this, what we do is, first of all, we identify the range of X that we're interested in. We then generate a grid that covers this range comprehensively. We generate predicted values from the model over this range using our grid. And we also calculate bands of standard errors. This gives us the 95% confidence interval, I'll explain this in a second, around the main fitted value curve that we're going to get from the predictions. And then we just plot all this together. So we plot the fitted curve and the 2 standard error bands, plus the predicted fit plus 2 times the standard error and minus 2 times the standard error. And this gives us our 95% confidence interval. And the results of this fit are shown in this diagram here. So the blue curve, the solid blue curve, which you can see here quite clearly, is the fitted values. And the dotted blue curves either side are the 95% confidence intervals. And as you've seen from the R code, we've simply calculated them as 2 times the pointwise standard error curves, which gives us an approximate 95% confidence interval of the fit. And there's some detail here you can look at as to why and how that works. But that's what I need you to know really, is that the main curve is solid, and to get the pointwise standard error curves, or the 95% confidence interval, we just take 2 times the standard error of the fit at each point. And what does the curve show? Well, the curve shows substantial non-linearity between air temperature and NOx concentration. So in other words, using this polynomial fit has been a good thing. We can see that from the estimated coefficients. They support the hypothesis of a 4th degree polynomial, and that curve looks to provide a fairly nice smooth fit to the data. And of course, a linear curve would not have this nice non-linearity that we can see here. We wouldn't get that with a linear curve. So it looks as if a polynomial regression has, in this context, done quite a good job. Now let's move on to step functions. Now, another way of inducing non-linearity is, rather than specify a polynomial, we can just cut the support of x, that is the range of x, into discrete subranges or bins, and then fit a constant model in each of those bins. So this essentially amounts to converting a continuous variable, in this case air temperature, into ordered categorical variables. And a piecewise constant model is then fitted in each bin, constant model, so we're just going to fit essentially a constant in each bin, like a beta naught in each bin. And that's going to result in a nonlinear model comprised of step functions. So what is a step function? Mathematically, a step function is a piecewise constant function having finitely many pieces for a variable x with cut points c1 to ck that cuts the data in the following way. So this is the step function c0 of x. It gives a value of 1 to observations where x is less than c1 and 0 otherwise. This is the step function c1 of x, the second step function. It gives the value of 1 to observations that where c1 is less than or equal to x and x is less than or equal to c2, and so on. And we just cut the data. We have these indicator functions that tell us whether the value of x lies within the intervals that have been defined by the cuts. So it equals 1 if the associated condition here is true, and 0 otherwise. And so for any value of x then, when we sum across c0x, c1x up to ckx, it must equal 1, since x must be in one of the k plus 1 intervals. It can't be in more than one, because they're mutually exclusive as defined by the step function. So a step function regression then can just be written in this form here. And of course all these variables are c1x1, c2xi, ckxi. These are just dummy variables. They're 1, 0 variables that determine whether the value of x fits within an interval or not. Now, because this model is linear in the parameters, we can estimate it in the normal way via least squares, so we're still in a linear parameters format. And step functions, before I say that, if x is less than c1, given this model, then our prediction is going to be beta naught, because all of these these step functions are going to equal 0. If cj is less than or equal to x less than cj plus 1, then we're going to have beta naught plus beta j, because we always have the intercept, but we're going to get a 1. If x falls within an interval, it's going to be 1, and we're therefore going to get the beta j, and we're going to add it on to the intercept. So it's as simple as that. It's just a dummy variable model. Step functions are very easy to work with and are useful when there are natural breakpoints in x. And notice that the good thing about a step function, unlike polynomial regressions, is we haven't imposed a global structure on the nonlinear function of x. We've split things into bins, and we're allowing differences across bins. In other words, if we change the fit in a certain bin, it doesn't affect the fit in other bins. It's not a global structure. It's actually a local structure. It's local to those bins. And that's one of the advantages of this particular method. Okay, so we fit a step function model with 5 breakpoints. In R, this is very simple. We specify a linear model, Nox is our dependent variable, and we simply tell R to cut air temperature according to 5 breakpoints, and that's going to give us 6 intervals, because of course the interval is k plus 1. Yeah. Summarize the fit, and that will show us our coefficients. We don't need to look at that because, again, we're not interested in individual coefficients. We're interested in how this fit looks across the support of X itself. So we generate predicted values. We use the same procedure we did earlier to generate confidence bands for the predicted values. That is 2 times the standard errors at the fit, minus 2. And then we just plot the results in the same way that we did previously. And we've calculated, therefore, the entire fitted function across a grid of values along the support of air temperature to map the relationship. 95% confidence intervals given by the dashed lines, which are so close to the solid blue line that they're quite difficult to see other than at the ends of the boundary intervals. So notice that the fitted function represents non-linearity. It's able to do it. It does it in not a dissimilar way to what we had before. However, unlike the function we saw before with the polynomial function, which is nice and smooth, this has undesirable bumps near the cut points. And so that's not something that we really want to see. But nevertheless, it does a good job at representing and showing us what the nonlinear relationship might look at. So it has got value. Okay, next part of the lecture, we're going now to move on to semi-parametric models. And essentially, they're going to combine elements from polynomial regression and from step functions.